This is my circuit. This system is designed to capture, process, and output HUD sounds using an electronic signal processing circuit. The acoustic signal from the HUD is first picked up using a microphone connected to a stethoscope and is then amplified, filtered, and played through a speaker. This allows subtle HUD sounds to be heard more clearly. Let's now take a look at how the signal is processed in each stage of the circuit. For simplicity, the schematic diagram is divided into 4 stages, with stage 1 from TP1 to TP2, stage 2 from TP2 to TP3, stage 3 from TP3 to TP4, and stage 4 from TP4 to TP5. We start with the pre-amplifier stage built around IC1A and a TL072 dual noise GFET op-amp. This op-amp is ideal for biomedical applications because it has high input impedance and low noise. This means it does not load the microphone and is able to preserve the tiny voltage fluctuations that make up the heartbeat signal. In this case, it is a fixed gain closed-loop non-inverting op-amp which provides a bandpass gain of 23 using the formula 1 plus R2 over R3. This will boost the low-level heartbeat signal, typically in the millivolt range, to a voltage level suitable for further processing. Since the op-amp only provides voltage gain and not current, it cannot drive a speaker at this point. Additional stages will handle that later. To prepare the input for amplification, C1 acts as a coupling capacitor which blocks DC offset from input and allows only the AC component, the actual heartbeat, to pass. The voltage divider made up of two 10k ohm resistors, R6 and R5, biases the op-amp to half of the supply voltage, which is 4.5 volts. This allows the op-amp to operate correctly in single supply mode, since we are not using a dual positive or negative power rail. Additionally, this stage includes a passband filter formed by R2, R3, C2, and C3. This filter allows only the relevant frequency range of the heartbeat to pass through while blocking low-frequency noise such as breathing and removing high-frequency interference like electrical noise. Lastly, the coupling capacitor C4 blocks DC and allows AC signals to pass through. With a cutoff frequency of 1.59 Hz, C4 ensures that any signal below that threshold is attenuated, while the heartbeat frequencies above it pass through clearly. This helps prevent saturation and distortion in the following amplification stage. Based on my readings for the amplifier in stage 1, we can see as the frequency increases, the gain will also increase until its maximum of 23 at 100 Hz as per calculated earlier on. Frequency more than 100 Hz will cause gain to decrease. Gain at 23 will be at 27.2 decibels. Based on the frequency response curve, the negative 3 decibel line will be at 27.2 minus 3 equals to 24.2 decibels. So the low frequency will be at 25 Hz and the high frequency will be at 1200 Hz. Therefore, the bandwidth will be 1200 minus 25 equals to 1175 Hz. The single supply mode will cause the negative side of the waveform to be cut. To prevent this, the level shifter, which is also the voltage divider, will shift the entire waveform upwards so that no waveform will be cut. To set up stage 1, firstly, power supply DC source is set to 9 volts and is connected to the circuit. Secondly, connect the function generator to the input of the circuit. At 1k Hz, using the oscilloscope, we will place channel 1's probe at TP1 while channel 2 probe at TP2. The output voltage is around 3.28 volts peak to peak. Set the frequency to 200 Hz without altering any other parameters. The output voltage is 4.4 volts, which is more compared to the previous voltage. The output voltage is higher at 200 Hz than at 1k Hz at stage 1 because the preamplifier is a bandpass amplifier. It is designed to boost mid-frequency signals while rejecting high-frequency noise like 1k Hz. We will move on to the next stage, which is the adjustable gain inverting amplifier, IC1B, the second op-amp in the TL072 package. This stage is configured as an inverting amplifier with a closed-loop negative feedback setup. Because it's inverting, the output is 180 degrees out of phase with the input. The key component here is the trimmer potentiometer P1, which allows us to adjust the gain of the amplifier. This is especially useful when the heartbeat sound is too soft or too loud, helping us fine-tune the signal for optimal output. Since this stage functions as a linear amplifier, it ensures the output remains within the limits and avoids saturation or clipping. The voltage gain of this stage is -10 using the formula -P1/R4. By adjusting P1, we change the value of RF and therefore control the amplification level. To allow the op-amp to operate in single supply mode, a voltage divider using two 10K ohms resistors R9 and R10 is connected to pin 5 of the IC. This provides a midpoint voltage and shifts the AC signal up from 0 volts so that both positive and negative parts of the signal can be processed without clipping. This arrangement also functions as a level shifter, helping to center the signal around half the supply voltage of 4.5 volts. This prevents the op-amp output from being clipped when it reaches the power supply rails. Finally, the output of IC1B is passed through C5, a coupling capacitor which blocks any DC offset, allowing only AC signal, the amplified heartbeat, to continue to the next stage for further filtering. At 1 kHz, we will put the output TP2 at channel 1 and all frequency as well as power supply to be left untouched. We will then place channel 2's probe to TP3 and get an output voltage of 6 volts. By turning the trimmer, we can see how it affects the output waveform. As I adjust the trimmer, the waveform will be amplified and at some point become saturated or cut off. Set the frequency to 200 Hz without altering any other parameters. The output voltage is 5.68 volts, which is relatively the same as the previous output voltage. As stated previously, as I adjust the trimmer, the waveform will be amplified and at some point become saturated or cut off. Stage 2 is a linear amplifier with a frequency-independent gain. That's why both 200 Hz and 1 kHz signals are amplified equally, resulting in similar output voltages. Now we move on to stage 3. For IC2A, a second IC TL072 is being used. Before the signal enters this stage, it passes through C5, a coupling capacitor that blocks any DC voltage and allows only the AC component of the heartbeat signal to pass through. To operate in single supply mode, a voltage divider made of R11 and R12, each 10K ohms, biases the non-inverting input of the op-amp at half of the supply voltage. It also acts as a level shifter to make sure no output is being clipped. IC2A is configured as a Sallen-Key second-order low-pass filter. This type of filter is designed to pass frequencies below a certain cutoff point while attenuating higher frequency noise. It helps isolate the hard sound frequencies by removing high-frequency interference that may have passed through the earlier stages. The filter is made up of two RC low-pass networks. Capacitor C7 will provide feedback loop. It helps smooth the signal near the cutoff frequency, allowing the desired frequencies to pass through while suppressing sharp transitions and noise. Finally, the output of IC2A passes through C8, another coupling capacitor that removes any remaining DC component. Since the lowest frequency can pass through a low-pass filter is 0 Hz, the bandwidth of a low-pass filter coincides with its cutoff frequency. Therefore, the bandwidth is 996 Hz, which can be found using this formula. Based on this table, when the frequency is below 100 Hz, the filter is at unity gain. However, when the frequency is at 100 Hz and above, gain and output voltage will decrease. Based on the frequency response curve, the -3 dB line will be at 0 - 3 equals to -3 dB. The high frequency will be at 900 Hz. Hence, the bandwidth would be equal to 900 minus 0 equals to 900 Hz, which is close to the cutoff frequency that we have calculated earlier on using the formula. At 1 kHz, keep TP3 at channel 1 and place channel 2's probe to TP4 and get a filtered output voltage of 4.15 volts. Since unity gain is not applicable as frequency is above 500 Hz, there is a drop of output voltage from TP3 to TP4. The output waveform at TP4 will be determined by the output at TP3. Hence, by adjusting the trimmer at TP2, it can also control the output at TP4. The frequency to 200 Hz without altering anything else. Since frequency is below 500 Hz, unity gain is applicable, hence output voltage at TP3 and TP4 is about the same. Just like previously, the output waveform at TP4 will be determined by the output at TP3, hence by adjusting the trimmer at stage 2, it can also control the output at TP4. Finally, we move on to the last stage, the power amplifier stage, which uses IC3 and LM386N-1 audio amplifier. This IC is responsible for driving the speaker, and unlike the previous op-amp stages, it is designed to supply current in addition to voltage gain. The IC is internally biased for single supply operation, so no external voltage divider is needed to shift the signal. Before the input reaches the IC, it passes through P2, a potentiometer acting as a volume control. Depending on how the potentiometer is adjusted, Pin E receives the full signal amplitude when rotated in one direction, while pin A and S set the lower amplitude or ground reference, allowing smooth control over output volume. The input signal is then passed through a coupling capacitor C13, which blocks DC and ensures that only AC signal reaches the amplifier input. This prevents unwanted DC from being amplified or passed to the speaker. On the output side, we have C15, a bypass capacitor which helps stabilize the amplifier and acts as a high-frequency noise filter, removing frequencies above 40 kHz. At 1 kHz, keep TP4 at channel 1 and place channel 2's probe at TP5. The output voltage is around 7.04 volts. By adjusting the trimmer P2, we can control the output at TP5. The final output will then be the maximum sine wave attained without being saturated. Set the frequency to 200 volts without altering anything else. The output voltage is around 7.36 volts. By adjusting the trimmer at PT2, we can also control the output at TP5. The final output will then be the maximum sine wave attained without being saturated. The IC in stage 4 amplifies whatever signal it receives from stage 3. Since the low-pass filter in stage 3 passes 200 Hz and blocks 1 kHz, the input to stage 4 is already weaker at 1 kHz, resulting in a lower output voltage.